A very good afternoon to all of you, those who have joined online as well as offline to this session on black carbon measurement as a tool for aerosol apportionment. I am very happy to share with you all that board has recently started a series of lectures on this very black carbon measurement, as all of us are facing a problem with this black carbon in our ambient air quality. So we have tried to discuss the intricacies of this and make our workforce more to better follow these measurements and equip ourselves in a better way. So in this series, today's lecture is second one, and that will be on brown carbon aerosol, a significant climate forcing agent in the Indian context. And we have a very eminent speaker with us from IIT Mandi, Dr. Sayantan Sarkar, and his PhD student, Ms. Supriya De. They will be discussing with the participants on this very topic. So I would request all the participants to have a big hand for our distinguished speakers. And now I would like to request Member Secretary of this board, Sri Chandrasekhar Ji, to deliver a welcome address to this session. Sir.
Respected Chairman, Sir, Bihar State Pollution Control Board, respected resource persons of today's training come exposure series, Dr. Sayantan Sarkar, Ms. Supriya De, both from IIT Mandi. Also today, Professor Ghazala Habib from Department of Civil Engineering, IIT Delhi has also joined, and a lot of people have joined online and offline here physically as well. So I take this opportunity to welcome all of you for this two-part lecture, training come exposure series. This is the second part of the training come exposure series. This is on black carbon measurement as a tool for aerosol apportionment. Into this air quality management, we all understand that aerosols are a major pollutant in the Indo-Gangetic Plains, and the state governments and various organizations are concerned about this. Especially the impact of the black carbon, brown carbon on health is being studied by various research institutions and research scholars these days. So this is very much a relevant topic, especially for the Indo-Gangetic Plains and especially for state like Bihar. And it's our pleasure to have our today's respected speakers, Dr. Sayantan Sarkar and Ms. Supriya De, both from IIT Mandi. So it's our privilege, and we are very much happy to have you today, and we are eagerly waiting to hear our lectures. With these few words, now I request our chairman, sir. Now I request Professor Ghazala Habib, ma'am, Department of Civil Engineering, IIT Delhi, to address the gathering, please. Ghazala Habib, please.
Yeah.
Forward.
Thank you, sir. Respected Member Secretary, Mr. Chandrasekhar, and other Pollution Control Board personnel, official, and participants of this lecture series. I welcome all of you. It's my pleasure to introduce such a gathering. It's a black carbon related series is very important for any part of the world, including India. As we all know, the black carbon is one of the very important or your significant component of PM 2.5 particulate matter, PM 2.5, because of its climate forcing effect, right? So the warming effect of the black carbon, and then its burn of cloud effect, of indirect effect in precipitation, all these are very significant effect, but poorly known or poorly understood. So such lecture series on black carbon and its apportionment, its scientific, uh, how it actually affects the climate, local air quality and health, would be very enlightening lectures for not only for scientific community, but also for regulatory body who are fighting to car very effective mitigation policies for reducing black carbon and PM 2.5. So I hope that this lecture series will enlighten many of us regarding current status of black carbon research, and will carve a path for new mitigation policy to formulate the new mitigation policy. With this, I would like to thank all of you, and I would like to invite the speaker, Dr. Satyan Sarkar from IIT Mandi to. Okay.
Privilege to introduce today's speaker to all the participants, though he needs no introduction, but we are very happy to have with us Dr. Sayantan Sarkar, who is an assistant professor in the School of Civil and Environmental Engineering at IIT Mandi. He is a doctorate from Jawaharlal Nehru University and has postdoctoral research positions at Wadsworth Center, New York, State Department of Health, USA, and at National University of Singapore. Dr. Sarkar is working on effects of aerosols on air quality. That is very much apt for us in present day scenario, climate and human health. He has also worked as an assistant professor in the Department of Earth Sciences, HISER, Kolkata. And his areas of interest is in-source apportionment studies, especially for atmospheric halocarbons and other VOCs, and reconstruction of pollutant deposition profiles from lakes and sediments. So we are very happy to have you, sir, and looking forward to a very interesting presentation. And joined with him, we have Ms. Supriya Day, who is a PhD scholar of Dr. Sarkar, working at School of Civil and Environmental Engineering at IIT Mandi. She has done her master's from University of Calcutta, and her area of work includes the sources, processing, transport pathways, and radiative effects of brown carbon aerosols in the eastern Indo-Gangetic plains. We are also very happy to have you, madam, with us, and again looking forward for your presentation very eagerly. So now may I request Dr. Sarkar to subject, yes, I have introduced you earlier, again for the benefit of participants. Again, I am Dr. Sarkar with his fellow presenter, Ms. Day, will be discussing with us on brown carbon aerosol, a significant climate forcing agent in the Indian context. So may I request Dr. Sarkar to please start with the presentation, sir.
Thank you very much. I'll share. Is the screen visible?
Yeah. Yes, sir. Yes, sir. But please put it in on the slide. So yes, this is fine.
Okay. All right. So a very good afternoon to all of you. Thank you, Mr. Chandrasekhar, Honorable Member Secretary, Bihar State Pollution Control Board, and all the officials at Bihar State Pollution Control Board, especially Dr. Saha, for kindly inviting us to talk here regarding our experience with brown carbon. Thanks also to Dr. Habib from IIT Delhi for kindly introducing the topic and emphasizing on the importance of black carbon in air quality research in the Indian context. So the overall theme of this seminar series is black carbon as a source apportionment tool. We are not going to talk about black carbon today. We are going to talk about something which is slightly different, brown carbon. When we talk about source apportionment of aerosols in India, we mostly look at those aerosols that have certain health effects. We have not really taken into consideration the radiative effects or the climate effects of these aerosols when we talk about source apportionment. This is something that it has been started to be done in other parts of the world. We have not started it yet, but probably in the future, this is something, a direction in which we might go. So we will be mostly focusing on something that has an important climate effect rather than a health effect. So we'll focus on the climate part. So our topic today is brown carbon and its importance as a climate forcing agent in the Indian context. We have divided the presentation into two parts. So I'll briefly talk about the basics of brown carbon, the importance, what is brown carbon, what are its characteristics, what are the sources, and why is it important for us to learn about. So that basic introduction I'll give in probably 15 odd minutes or so. Then Supriya will take over and then she will talk mostly about the measurement aspects and she will share some data that we also have from the eastern part of Indo-Gangetic Plain so that the entire picture becomes clearer to us. Okay, so with this background, let us start. So we'll first briefly talk about aerosols, the effects of aerosols on climate forcing. This is a very well-known figure now. This is from the latest IPCC report that has come out very recently, IPCC Assessment Report 6. This basically shows us all the, let me just take out this pointer. So this shows us how important have different species been in effective climate change on a global basis. So the 0 is here, the positive values indicate warming. So anything that has a positive forcing indicates warming. Anything that has a negative forcing indicates cooling. So we all know that carbon dioxide is the largest contributor to climate change, a very high positive radiative forcing. Then you have methane, nitrous oxide, other halogens. But our focus is here, which is the aerosols part, which is here. So first of all, we see that the aerosols have a negative effect on climate change in the sense that they cool the climate. So we can think of it this way, that while the greenhouse gases are warming up the climate, the aerosols are sort of countering that warming. They're cooling the climate to some extent. This is good in itself, but we all know that aerosols are not good per se. They have health effects, they have air quality effects, haze, and so on. So we have to reduce these concentrations to a significant degree. But the part that I want to focus on is that if you look at how uncertain these measurements are, which are sort of shown by these bars here, for carbon dioxide and methane and others, the uncertainties are quite small. So we are quite certain as to how good they are or how strong they are in terms of affecting climate. If you look at aerosols, on the other hand, we see that the errors, the uncertainty is very, very high. So this is because a lot of things about aerosols, how they are incorporated into cloud droplets, how they affect cloud reflection of radiation, how they affect cloud lifetimes. All these things are very, very uncertain. So our understanding of the aerosol climate effect is quite uncertain at the moment. Now, if we look at sort of the individual components of aerosol, this is all of the aerosols taken together. But all of us know that aerosols are nothing but a mixture of a large variety of different chemical compounds, black carbon being one of them, sulfates, nitrates, organic carbon. These are major components of aerosol. So we know that overall the aerosols cool the climate, but how do the individual components affect climate? Do all of them cool the climate, or there are some of them that warm the climate and some cool the climate, and the result is somewhere in between? So when you ask that question, then we find something like this. This is the same radiative forcing that is shown here, but now we have divided the aerosol part into the major constituents. So you have the total aerosol forcing here, which is negative, overall cooling, which counteracts the warming. Then this aerosol is made up of sulfate particles, nitrate particles, black carbon particles, and organic carbon particles, which are all here. So this tells us that yes, the overall forcing is negative. It causes cooling, and the cooling is mostly due to sulfate, which is here, which is the largest contribution. And then you have some amount of nitrate also that does the cooling. On the other hand, you have black carbon aerosols which warm the climate. They absorb the sunlight across wavelengths and then they warm the climate. So if the black carbon concentration increases, this forcing value will also increase. And as a result, the total negative effect of aerosols will sort of try to go towards this number. So it will become more and more positive in the future. So that's a problem. But black carbon is not something that we are focusing on today. We are focusing on this part. So this is the organic carbon part. So the problem with organic carbon is that its climate effects are relatively very uncertain. So our understanding of how important organic carbon is in terms of affecting climate is not very certain. We thought initially that organic carbon mostly scatters light away and as a result cools the climate. But recently, in the last decade or so, our understanding has evolved and we now understand that there is a fraction of organic carbon that actually absorbs sunlight. So this part actually causes warming just like black carbon does. So this is comparatively new, this understanding that there is a large fraction of organic carbon that actually absorbs sunlight and therefore warms the climate just like black carbon does. So we have a need to better characterize the climate effects of organic aerosols. So this is what we are going to talk about, the importance of carbonaceous aerosols and brown carbon here. So first of all, definitions in terms of names. We know that this soot, we also call it by the name of elemental carbon or black carbon, but there's a sort of academic definition that is given to them, that which part we will actually call elemental carbon and which part we will call soot. That definition is mostly dependent upon the method by which we measure these species. If we measure the light absorption of the elemental form of the carbon, then we call it black carbon or BC. So this is what the atherometer does. For example, the first talk I understand was on the atherometer. So the atherometer measures the black carbon concentration as a function of its optical properties, by its light absorption properties. So we call that black carbon. On the other hand, that same substance, if you measure using its thermochemical properties, meaning its resistance to temperature for degradation, then we call it elemental carbon. So then we have a spectrum here. So that spectrum of carbonaceous aerosols goes from organic carbon, which is very, very vulnerable to temperature. It breaks down very, very quickly, to something which is not at all vulnerable to temperature, which is elemental carbon. On the other hand, if you look here, then that same organic carbon scatters light and therefore is whitish. The black carbon absorbs light and therefore there is black. In between, we have something that are colored organics, in the sense that is, they are organic molecules that absorb sunlight, and these are brown in color. So this is where brown carbon comes from. So there's not a distinct definition of this, but it's a spectrum. On one end, you have white, colorless, scattering organics. On the other hand, you have black absorbing brown carbon. And in the middle somewhere, you have slightly absorbing brown organics. So these are brown carbon. So brown carbon is nothing, as I said, but the organic fraction that absorbs light. Previously, organic carbon was thought to be entirely scattering in nature, therefore cooling the climate. But this part actually warms the climate. Now, what are the effects? If something absorbs light, then it will have a direct climate forcing. It has been found that brown carbon absorption can be as high as 40% of black carbon absorption. So yes, we spend a good amount of time, we spend a good amount of resources on measuring brown carbon because it's quite important as a radiative forcing agent. But brown carbon in some cases can be very, very significant also with respect to black carbon. There is one curious thing about brown carbon, which is the nature of the light absorption is very, very distinct. So black carbon absorbs sunlight across all wavelengths, shown by this black line here. Brown carbon absorbs very strongly only in the UV and the low visible ranges. So this means that this molecule or these molecules can absorb this certain fraction of light very, very effectively, and therefore the amount of UV that will come into the troposphere, the amount of UV that will come to the surface of the earth and therefore drive tropospheric processes, tropospheric chemical reactions, that part will reduce over time if brown carbon increases over time. Just like black carbon can be deposited on glaciers and therefore affect snow melt, brown carbon can also get deposited on glaciers and affect snow melt. It's the same process. They absorb light, the snow warms up and melts, As a result, the underlying soil becomes exposed, that soil absorbs more sunlight, and it becomes a cycle. It becomes a feedback loop. Now, the other major difference between black and brown carbon is that black carbon has more or less standard sources. We have a pretty good idea what the sources are. So fossil fuel combustion is a major source. Biomass burning is a major source. The tricky thing with brown carbon is that these are literally hundreds and thousands of organic molecules that have come together which share this common property of light absorption. And they can come from a large number of sources. They can come from biomass burning. They can come from burning of petrol and diesel. They can come from conversion of gases into particles in the atmosphere. They can also come from emissions from phytoplanktons, marine emissions. So there are a large number of sources. So the problem that we have in our hands is that there is large variability depending upon the type of fuel, the type of chemical that is causing this brown carbon to exist, which is called a precursor. The nature of the combustion, whether the fire is a flaming fire, it burns with a visible flame, or it burns with a smoldering flame, and how much time it spends in the atmosphere. The greater the amount of time it spends in the atmosphere, the more its properties change. So if you come to the Indian context and you find that there are regions in India, especially in the Indo-Gangetic plain, that are industrialized, that have a lot of population, and then there are regions that are sort of pristine and remote. So then brown carbon, once it is emitted from these industrial regions and agricultural regions, they will be transported by the atmosphere, and then their properties will change over time. So this is atmospheric processing. So receptor locations, rural locations, remote locations that do not have any sources by themselves will always be affected by this atmospherically processed brown carbon that is transported also from the local inputs. So this is the problem that we face in terms of accurately characterizing it. A good example would be the transport of brown carbon to the Himalayas in the Tibetan plateau. So entire Indo-Gangetic plain is responsible for a large amount of biomass burning and fossil fuel combustion, and the brown carbon can be emitted, transported by the air, and deposited across the glaciers in the Himalaya and in the Tibetan plateau, thereby affecting climate. So it's not a local pollutant. Its effect is spread over large regions, large geographical stretches, stretching about thousands and thousands of kilometers. Now, if you quickly look at the properties, we'll see that there are natural sources of brown carbon. There are trees which emit certain chemicals, certain gases, certain volatile organic compounds in the atmosphere. These gases react with whatever is there in the atmosphere, especially oxidants, and then they convert into particles. So these are the secondary organic aerosols. On the other hand, the brown carbon can directly come from industries, can come from domestic fuel use, especially if it's a biofuel, from cars, and so on and so forth. There's a natural component, there's an anthropogenic component. And the characteristic that makes this difficult to analyze as compared to black carbon is the wide variety of the type of molecules that make up brown carbon and the wide variety of reactions that they can undergo while they're present in the atmosphere. So this is just one set of reactions that these VOCs can undergo in order to produce brown carbon. There are many, many hundreds and thousands of more such reactions that produce this. So it's very difficult for us to have a clear understanding of what we are looking at here. In addition to the nature of sources, meteorological parameters, especially temperature, moisture, sunlight, all of this lead to changes in the properties of brown carbon. It is found that in some cases, the sunlight bleaches the color out of the brown carbon, which means that the absorption property decreases. In some cases, the presence of sunlight enhances the absorption property. So it's a question of finding out that in a particular region, let's say the Indo-Gangetic plain, which has source regions, which is, for example, agricultural residue burning, forest fires, industrial sources, urban sources, domestic household sources, as well as areas which are rural and remote. Depending upon the location, how does the nature of the brown carbon change, and how does the property, the light absorption property, the climate forcing property of brown carbon change? So this is why it's important. So spatially and temporally representative field measurements are required. Just like we need field-based measurements for black carbon on a large spatial resolution, on a large temporal resolution for a good period of time, similarly, brown carbon also requires this spatially and temporally representative field-based measurements. Just to give you one example of the effect that it has on photochemistry, this is simply the effect of brown carbon on the production of oxygen radical, the oxygen atom from the NO2 photolysis, and thereby the production of tropospheric ozone. So it is seen that the presence of brown carbon over Asia reduces the NO2 photolysis rate by about 8% and reduces ozone concentration by about 6% at the surface. So this is a direct link between a pollutant, which is primarily a climate forcing agent, to an effect which is primarily an air quality effect, which is the presence of tropospheric ozone. These two are interlinked. So the point that I want to make here is that pollutants that affect air quality and pollutants that affect climate are not necessarily separate. They are interconnected in a very, very complicated network. And understanding one is very important for understanding the other. This is shown by here also, the background levels of ozone in the absence of black and brown carbon. In the presence of black carbon, the ozone production remains almost the same, but in the presence of brown carbon, which absorbs in the UV range that is required for ozone formation, the ozone production decreases very significantly. So overall, globally, it is found that it inhibits surface ozone production by 18% and also has a tremendous effect on the hydroxyl radical production, which is very important in terms of photochemistry. Now, before I hand it over to Supriya, I will just set the context of what brown carbon studies have been in India, what they look like, and what is the special sort of distinctiveness of the eastern part of the Indo-Gangetic Plain that we are looking at. So this figure basically shows some of the work that has been done on brown carbon in India. There are others, but we are mostly focusing on the Indo-Gangetic Plain. So as you can see, there have been reports from source regions, for example, Patiala in Punjab, where there is a lot of agricultural residue burning, especially in the post-monsoon. You have Delhi, you have Kanpur here, and in the eastern part, you have these receptor locations which do not have a lot of sources, which is Eastern Indo-Gangetic Plain, Kharagpur here, and the Bay of Bengal. So what we find here is that the brown carbon that is emitted in this region is very, very strongly absorbing. The molecules are very, very strongly absorbing. As the winds transport them towards the Eastern Indo-Gangetic Plain and into the Bay of Bengal, they are bleached by sunlight, but a significant portion still remains. There is significant amount of bleaching, no doubt, but a significant absorption still remains. So over this stretch of about 2,000 kilometers, what is emitted in the northwestern part of the corridor affects the air quality and climate in the eastern part of the corridor. So this is why the importance of the Indo-Gangetic Plain must be apparent to all of us, that the Indo-Gangetic Plain is a region that is very significant, not only in terms of emission, but also in terms of affecting the entire air quality and climate of that entire belt in one go. So the major sources are, of course, agricultural residue burning, household uses of fossil fuel, and these small-scale industrial units that do not have any emission control mitigation measures. So if you look at the way fire spots are distributed in India, so these are all agricultural residue fires that are happening in India. In summer, you have this entire subcontinent covered with fire spots, but the air mostly comes from over the marine sectors. So this does not bring biomass burning emissions to the eastern part. In the post-monsoon and winter, on the other hand, the air comes from this entire Indo-Gangetic Plain, thereby bringing all these emissions along with all the black and brown carbon that are being emitted here to the eastern part of the corridor. This is why a corridor-wise air quality intervention, a corridor-wise air quality management policy is required, because if you have policies that are designated for local regions, then this transported component will be totally forgotten. So I hope that the effect of the, or the distinctiveness of the Eastern Indo-Gangetic Plain is clear to us now. So I will now hand over to Supriya, and then she will talk about the measurement part, that how do we actually measure and what are our findings. I thank you very much, and I ask Supriya to kindly share her screen.
My screen is visible.
Yes.
Okay, good afternoon, everyone. I'd like to thank all of you to invite me for this talk. I'm going to talk about this aerosol brown carbon measurement specially. So starting with the aerosol measurements, there are two major kind of aerosol measurement. One is time resolved online measurements, including the atherometer, aerosol mass spectrometer, scanning mobility particle sizer, etc., where the brown atherometer and aerosol mass spectrometers can measure the brown carbon, but in those instruments, the uncertainty is much higher for brown carbon measurement. On the other hand, we have traditional time integrated offline measurements where we have collected filters and then we have extracted them and analyzed in UV-Vis fluorescence spectrometer, TOC, OCC analyzer, ion chromatography system, etc. So there is some pros and cons of these online and offline measurements. Online measurements are relatively novel and new. They have short integration time and then they are very useful for low concentration ambient particle measurements. Also, they are suitable for measurements in the moving platforms like aircraft, trains, cars, etc. But the major drawback is they require the daily maintenance. Their uncertainty based on are higher because the data generated from these instruments are based on multiple assumptions and also they are very costly. On the other hand, the offline measurements uncertainty is extensively studied. So the uncertainty is relatively low as the measurement has done on the realistic atmosphere. The time resolution of offline measurements varies from few hours to days. But they are somehow, the drawback here is they are somehow some volatile species cannot be measured by these offline measurements because the volatile species has very short lifetime. So they can emit in the atmosphere and they cannot be stay in the atmosphere for a certain amount of time. And also the offline measurements are time-taking process, but they are cost-effective. Now we are mostly focused on these time-integrated offline measurements, and I am now going to show you how we have collected these brown carbon measurements and how analysis these measurements have done. So this is the okay. So these are the PM2.5 samples collected in the quartz microfiber filter. So these quartz microfiber filters are previously baked, and then we have collected these PM2.5 samples. Then we measured their mass by gravimetry. After the measurement, we stored those samples, and when we have analyzed those samples, a bunch of filter can be measured for OCC content by thermal optical analyzer, and the residual part are extracted in ultra pure water or methanol or by any other organic solvent by sonication process, and to get the water the water and methanol soluble fraction. After this, we have measured the water soluble organic carbon by TOC analyzer and different ionic species concentration by ion chromatography system, and we measured those optical properties of brown carbon extracted from these water and methanol solvents. We will measure their UV-Vis and fluorescence signatures also. So these are the main optical parameters which are measured from this UV-Vis measurement. One is the absorption coefficient, angstrom exponent, mass absorption efficiency, complex refractive index. I'm going to talk about these individual parameters in my next slides. So absorption coefficient is basically an ability to absorb light by compounds. So here the absorption coefficient is measured by this formula where A is the absorbance at lambda wavelength, and A700 is the absorbance at 700 wavelength. VL and VAR are the volume of liquid and volume of air, and L is the path length. So when we measured this absorption coefficient in our study location, we have found this is our result. Here, x-axis is the wavelength and y-axis is the absorption coefficient.
I think your screen is not moving. What you are presenting, that is not moving. It is stuck with that flowchart, a schematic flowchart.
Okay, let me reshare then.
It's visual here.
It is visible here.
No, the current slide that she is saying, that is not moving. It is stuck.
Oh.
Supriya, you can reload your presentation.
Yeah, sure.
Okay.
So now you can see.
So it is still showing the flowchart, not the one that you were explaining about the absorption and all this.
But now it is reloaded. Now.
No. What she is saying, it is in the next slide. It is still stuck with the content that is there. It is in the.
She was talking about.
Actually, it is visible to me also. This
For
definition
us also it is visible.
Yeah, it is visible to me also.
The graphical part.
Yeah.
It is visible to us.
And even the cursor.
I
Okay.
think mine-
Everyone.
Okay.
Go
Okay,
ahead.
go ahead, Supriya.
Okay. So in our study location, we have found that higher absorption is found during winter and post-monsoon season compared to summer. And this post-monsoon and winter, as Sir has said, that air mass are mostly coming from the northwestern part of India, where there is extensive biomass burning and crop residue burning has happened. So due to the long-range transport and also some local emission, the strong brown carbon chromophores can emit in this location during post-monsoon and winter season. So the absorption gets higher. In this left-hand side figure was taken from Chaudhary 2021, where y-axis is the beta abs and x-axis is the wavelength also. And here they compare with different crop burning, the emission from different crop burning, the brown carbon versus black carbon. And it is clearly seen that brown carbon shows very strong absorbance in the lower wavelength region comparatively, where the black carbon shows the absorbance in the higher wavelength region. So the another important parameter is the angstrom exponent, is basically the spectral dependence of light absorption from chromophores in solution. It is expressed with this equation. And if you look into this figure, this brown carbon angstrom exponent is much higher comparatively black carbon. Black carbon angstrom exponent lies in 1, whereas brown carbon angstrom exponent here varies 3.6 to 4.5. So it shows strong wavelength dependence in the lower wavelength. But it depends on particle size, chemical composition, coating, and possible morphology throughout the location, throughout the season also. So moving to the next, mass absorption efficiency, it's basically the absorption measured per unit brown carbon mass. So this is the formula beta abs by m, where m is the organic mass. So in our study, we have found that nighttime absorption is nighttime ME is much higher comparatively daytime ME throughout the season. But again, the post-monsoon and winter, there are strong brown carbon chromophores present, and due to this biomass burning emission and long range transport, which has happened here. So when we compare this mass absorption efficiency of brown carbon and black carbon, it clearly visible that at 370 nanometer, which is basically the lower wavelength region, the brown carbon are much higher mass absorption efficiency than black carbon. On the other hand, black carbon again show the major for absorbing agent in the higher wavelength region. Now, this brown carbon emits from biomass burning and crop residue burning, but their absorption efficiency varies. So this study was done by Cheng et al. 2011, where they perform different types of species like corn, wheat, elm, pine, etc., and they measured their absorption efficiency, and it's found that the absorption efficiency from wood burning are much more higher than the crop residual burning, and whether the diesel is the black carbon emit from this fuel are much higher absorption efficiency. But this is a chamber study. This is not the study from real atmosphere. So it's highly useful that with atmosphere also. Now the most important is the complex refractive index, which determines basically the amount of light gets absorbed or scattered, and is expressed as the n+1 ik, where n is the real part. It's basically associated with the scattering effect, and in the visible region it's wavelength independent, and the mass and the range is for aerosol is almost stable, 1.5 to 1.7. On the other hand, k is the imaginary part of this refractive index, and it's mainly associated with the absorption, and it strongly depends on the wavelength, and it varies with the wavelength. So in this figure, this is our study where we have compared complex refractive index throughout the season and with varying solvent. So here y-axis is the complex refractive index and x-axis is the wavelength. Here we have found that summer is the lowest refractive index comparatively post-monsoon, and also methanol is the methanol shows highest refractive index comparatively water. Now, recently, Saleh et al. 2020 have categorized this absorbing efficiency of brown carbon into different Okay, so Saleh et al. Compared this, categorized this brown carbon by their absorbing nature. So this plot is basically y-axis with angstrom exponent, and x-axis is the log scale of refractive index at 550 nanometer, that is the visible wavelength. So they categorize as very weakly absorbing BRC and strong absorbing BRC, and black carbon lies here. So it clearly visible that visible wavelength, there is a strong refractive index and lower angstrom exponent. Also, when we come from this to this, towards the black carbon and strong brown carbon chromophores, there are large molecular size which can be found in the strong brown carbon chromophores. Their volatility could be lower. The solubility also varies with solvents. Now, from this figure and this figure, we have found that in the visible location, visible region near 550, the refractive index of our sample lies in this region, that is weakly absorbing BRC and moderately absorbing BRC. Now, complex refractive index has been calculated as rho lambda into MAE by 4 pi, where rho is the density, and it is assumed that 1.5 gram per centimeter cube for water and methanol extracts. So these are the parameters, and now I am focusing on this, their importance in the climate forcing model. So these 4 parameters like beta abs, angstrom exponent, mass absorption efficiency, complex refractive index, they all serves a great role in the radiative forcing, because radiative forcing radiative forcing of brown carbon is mostly model oriented, and therefore the prediction somehow could not be matched. So this is the field-based regional values. which can provide more accurate prediction in the radiative forcing model. We have calculated the relative radiative forcing of brown carbon with respect to elemental carbon. This is the formula we have used here. Here I0 is the solar irradiance, H is the boundary layer height, C is the concentration of water soluble organic carbon and elemental carbon. And we have found this result here. So in this figure, the x-axis is the wavelength and y-axis is the relative radiative forcing in first half and second half solar irradiance. So this red one is the solar irradiance in summer, which is higher, and post-monsoon and winter has lower solar irradiance. But in terms of radiative forcing fraction, winter and post-monsoon shows higher forcing fraction comparatively summer. And then it's also indicate that this forcing at the lower wavelength region could belong to this highly absorbing brown carbon chromophores. Another very recent study has done this direct radiative forcing. They have also found a very significant amount of brown carbon or absorbed light around 300 to 400 nanometer region, and as comparatively elemental carbon, and from their study it goes up to 60%, which is not a non-significant absorption, forcing. So overall, this brown carbon forcing cannot be neglected in the upcoming years. Now I am going to talk about fluorescence property. It has been found that brown carbon shows their fluorescence nature also. Fluorescence is basically a very intrinsic property and is a form of luminescence where the particle excite at lower wavelength and emit in the different in the longer wavelength region. By checking their emission wavelength, which is particular for different compounds, we can identify these chromophores. So by using this fluorescence property, brown carbon chromophores are categorized as aromatics, proteins, humic-like substance, and other organic matters. So we have performed a 2D fluorescence throughout the season in our sample. And here y-axis is the fluorescence intensity and x-axis is the emission wavelength. But this 2D from this 2D fluorescence, we cannot extract all the information. It shows a very broad peak around 380 to 440 nanometer region. Usually this peak, this region peaks belong to the humic-like substance. But if there is another kind of compound there, low intensity fluorophores are there, we cannot we cannot know about this from this 2D fluorescence. And here we have measured the 3D fluorescence, which is basically a excitation emission matrix. The y-axis is emission wavelength, x-axis is the excitation wavelength, and this is the color bar represents their intensity. So in the varying intensity in this matrix, we can found the low intensity as well as high intensity fluorophores. So in this figure, taken from this Wu et al. 2021, they have categorized them like protein and humic-like substances, and the protein-like substances like tyrosine, tryptophan, marine humic-like, they are mostly present in the lower wavelength region in both excitation and emission wavelength, but humic-like substances are majorly present in the higher. On the other hand, peak T, peak M, and peak B belong to these protein-like substances. So it's by using these 3D fluorescence, we can identify these brown carbon chromophores very clearly. So overall, despite a major polluting region, these brown carbon studies are mostly concentrated in the source region of IGP. The studies are very limited in the eastern IGP, like in a receptor location type and rural type also. The major source of this eastern Indo-Gangetic plain are the fossil fuel, biomass burning, marine, and as well as secondary. So overall, this brown carbon contribution throughout India is not a negligible, not negligible amount, and it may hamper we can consider it as a potential climate forcing agent in the upcoming years. So we should think about these brown carbon studies extensively throughout the India to understand their nature. So these are the reference I have used here. Thank you.
Thank you, Ms. Day. So we have very nice presentations by Dr. Sarkar and Ms. Day. So again, a big hand for them, both of them. And now the floor is open for queries and discussions or any clarifications. Dear participants, if you have any, please come forward.
Supriya, slide to छोड़ी दे. कैमरा को ऑन कर दे. हाँ, good.
तो अगर किसी का कोई प्रश्न हो, हाँ, डॉक्टर कृपाराम सर.
Yes, Triparamji, you are open. Your floor is all yours.
You are not audible, sir.
डॉक्टर कृपाराम सर, प्लीज आपका क्वेश्चन बताइए.
You are not audible, sir. I think some issue with your connection.
Safety, Dr. Safety.
You can go to next.
Yes.
Okay, so I think he might not be having. Am I audible?
Yes, sir. Yes, sir. You are welcome.
Okay, so thank you to give this beautiful demonstration of your work. So I do know Sayantan, I have been following him, but I have not officially never met with him. So I would just like to ask one thing with Dr. Sayantan, if he just like, what is the importance of chromophore, that the fluorescence activity that we are doing, like with that particular, what kind of information we are getting out, like? I've not done that, so I'm more curious to know, like on the research side, why is it important to carry to do this extra supplement thing when we are doing brown carbon?
Okay, yeah, thanks, Dr. Saifi. So the point here is that when we do measurements of brown carbon, when we extract them into water and we measure the optical properties, the light absorption properties, we are basically getting a response that is bulk in nature, in the sense that all the molecules that are there that absorb light, they are coming together to give you a joint response. So we don't know that out of these molecules, which ones are the ones that are causing a good amount of absorption, which ones are causing moderate absorption, which ones are low absorption or not. The second thing that we don't know is that where are these molecules coming from, or what type of molecules that they are causing the absorption. So the UV visible part only tells us how much absorption is there. So the fluorescence part actually tells us to some extent, not to a very high degree, but to some extent, what types of molecules are there. So when we rather than taking a 2D fluorescence, that is by fixing the emission and the excitation wavelengths, we do a scan of the entire wavelength range. Then all the potential molecules that absorb light in this entire wavelength range, all of them contribute. And then this matrix is broken down by this model, which is called parallel factor analysis. That model basically tells us that there are these categories of chromophores, these categories of fluorophores that are absorbing in different regions. So one of these categories can be humic-like substances. Within the humic-like substances, there can be 2 or 3 different categories. One of the categories can be protein-like substances. So then we have some understanding that, okay, the brown carbon total absorption might be apportioned into these humic-like substances, protein-like substances, and so on. So that is the main idea.
So can we quantify also like that in say, like how much is the contribution?
Yeah, so we can sort of quantify the contribution of each of these individual categories to the total fluorescence activity, fluorescence intensity. We can quantify that, and we can say that, okay, over summer, let's say that 60% is coming from protein, 40% is coming from humid-like substances, so on and so forth. It can be done, yes.
Okay. Okay.
That if these biomass are contributing to brown carbon, then when we talk about to having alternate fuel in the form of biomass pellets, they are the process pellets. So will not be they contributing to this brown carbon? So whether it is whether it will be appropriate to go for that?
It is. I mean, the thing is that biomass, whenever we burn it in whatever form, will release organic carbon into the atmosphere. Whether it will release a lot of black carbon as compared to brown will depend upon the temperature at which it is being combusted. If
Right.
it's burning as a fire, then it will produce more black as compared to brown. If it's burning, like for example, when we have these household chulhas that use charcoal that sort of smolder, they do not flame, but they sort of give a smoldering fire, then you will get a lot of brown carbon. So,
Right.
I mean, in whatever form we use biomass, we are bound to produce black and brown carbon, but the relative amount will depend upon the type of combustion that is happening.
That is fine, but it will be contributing to the air pollution.
Certainly.
Sir.
Yes, of course. Yes.
Sir.
Yes, if you burn biomass, it is definitely going to contribute.
Sir. Thank you. Thank you. Yes, Sahasa, please.
Wonderful lecture. Welcome. Beautiful. Total professional. Now the thing is that Priya told that it has an impact in rural areas. I was there with the Taj Mahal for about 10 years. And that time I was doing research on the impact of air pollution on Taj Mahal, impact of Mathura refinery on its emission of Taj Mahal and all things. And that also I heard the name of this brown carbon. And but the impact, the way the papers were written, one cannot say it is the brown carbon is impacting the coloration of Taj Mahal carbon. In my opinion, because I stayed long time at Taj Mahal and I used to visit Taj Mahal in different things, and to my opinion, it's an illusion. If you see Taj Mahal in the morning, you will have one picture. If you see the Taj Mahal after the rain, it will have another picture. If you see the bright moonlight, it will have another picture. So I was really confused. But what is your opinion on the browning of Taj Mahal marble due to brown carbon? What is your opinion? Just I wanted to please.
So, my understanding is that the fact that the discoloration happened in the museum itself is because of the simple reaction of acidic substances corroding the marble. So that is the major fact. I mean, I don't think that brown carbon has any direct role in the discoloration of the monument, but what it does is that if you take a photograph from a distance and the air that is between you and the Taj Mahal has black or brown carbon, then that light will be absorbed, so it will become hazy. The reason that we cannot get clear pictures is because there is something in the air that is absorbing the light. It can be black, it can be brown, it can be sulfate nitrate. So visibility reduction basically. But on the monument itself, the discoloration, I don't think it has anything to do with the presence of brown carbon at least. Yes, there might be deposition of aerosol particles on the surface that will lead to some sort of darkening. That is probably the case. But I cannot say anything for sure. I have not looked into this topic in great detail.
Okay, thank you. So the next, what I did with the help of National Metallurgical Laboratory, Jamshedpur, we have installed some corrosion studies. And I told that time the professor DPN Singh, that time he was looking after that division at Jamshedpur. So he installed some corrosion rack with different types of material, marbles, metals, etc. And I told him, I just had a presumption and assumption, because River Jamuna is contributing H2S into the atmosphere and not the SO2 is causing. So it was again, he took up this study, and there is a paper in the Nature also, written by me partially and partially by Professor Didion Singh. And there we have demonstrated it is H2S that is causing the deterioration of the color and corrosion effect on the marble. I will refer that paper to you. So that is a very interesting paper
Yes,
and
sure.
how they have studied. And you
Yes,
know,
sure.
Didion Singh is a very renowned professor and Bhatnagar Award. He has
That
retired
would
from.
be interesting. Yeah, I have not personally studied this issue a lot, but yeah, that would be very interesting.
Because the impact of our monuments is rightly not being discovered and studied properly. This is my assumption. Thank you so much, Sayantan.
Thank you, Dr. Sarkar. So,
Kriparam is there.
Dr. Kriparam, sir, are you there? So, और कोई क्वेश्चन किन्हीं पार्टिसिपेंट्स के द्वारा?
I want to like to know,
Sir.
myself is Chandrasekhar,
Sir.
member secretary here. Just out of curiosity, would like to know one thing. What will be the nature? What is the nature of the effect of black carbon or brown carbon on the rainfall? Because what in my opinion, is that the particles should act as a nuclei for rain droplets. So, in what way it affects rainfall, whether it decreases or whether it increases the rainfall in a particular region? Because on one hand, various governments are attempting to go for artificial rain. So, in what way this will affect the rainfall pattern or a particular rainfall in a particular region? Just out of curiosity, please.
Okay, so I can sort of give a qualitative answer to this. The answer is that the effects of black or brown or any other aerosol particle on rainfall is mostly mediated by what you mentioned, is that they act as nuclei to form clouds. So generally the understanding is that if you have a lot of these particles in the atmosphere and you have water that can condense on these particles, then you will have a lot of clouds. So the clouds then will reflect the radiation away, and as a result, the climate will sort of cool down a bit. Now, that is one effect. The other effect is that if you have a lot of aerosols, then the same amount of water gets distributed into a lot more number of cloud droplets. And as a result, each cloud droplet is not large enough to fall as rain. So previously, the number of droplets were small, but the droplet size was large so that they could fall as rain. But now the droplet number has increased, but the droplet size is very small. So they have not reached that critical mass to fall down as rainfall. So then what it does is that the cloud lifetime increases, but the rainfall is suppressed. The clouds stay in the atmosphere for a long time, but they do not fall as rain. There is one effect. There is also another effect, which is that if you have these nucleus, the black carbon acts as the nucleus, then you know that black carbon absorbs light and there will be water on the surface. So when it absorbs light, the water will heat up and it will evaporate away. So then the cloud lifetime also reduces because the clouds form and they are sort of burning off. The black carbon becomes so hot that the clouds burn off. So these are sort of competitive processes that happen at the same time in the atmosphere. Now, which of these processes will dominate depends upon a large number of things, and the final result, generally models are able to predict that what will be the effect on rainfall, will it increase or decrease. But qualitatively, these are the background in which these things happen.
And so thank you so much. Again, related to the same issue, I would like to raise one question, sir. Actually, of late, what I have observed here in Bihar is that of late, due to lightning, a lot of people are dying. This is happening in the past very few years. So what I am relating is that whether the pollutant aerosols is responsible for some cloud formation or due to some unusual sort of a cloud formation, lightning is happening, because of which more death is happening.
Is it predominant in West Bengal?
Maybe, sir, just for thought. Yes, sir.
Lightning part, I will not be able to tell you in very much detail. The thing is that the fact that like heavy storm frequencies have increased in certain parts of India, especially coastal India, it is thought that it is because of climate change, that the climate is warming up, so tropical cyclones have increased. And associated with it, there are these lightning events and so on. But if you talk about continental India, which is not affected by these tropical cyclones, then I cannot really tell you a particular reason linking air pollution with lightning events. I am not very sure about this at this point of time. I have seen some papers that say that lightning events have increased over time, but
Yes.
how to link it with air pollution, I am not very sure.
So just for your information, sir, I'll also provide you the data also to you, sir. In the past 2 years, the number of lightning incidences are increasing, and the death due to lightning is also, the figures are increasing. We have obtained this information from the State Disaster Management Authority as part of some other study which we are conducting. So this may be of interest, sir. You can look into this. Whether is there any such influence of black carbon or brown carbon, maybe, or some other thing.
Okay.
Something is happening in an atmosphere, and the causes something related to some particles, maybe, or due to some gases, maybe. But cloud, when we speak about lightning, definitely it's about clouds. So the nature of type of clouds, or maybe the morphology of clouds, is being influenced by some particles. Maybe particles are like what you have been mentioning, that it affects the cloud formation. So maybe this may be linked and be thought about.
Yes.
Yeah. Thank you,
Supriya,
sir.
you would like to add something to this? Your background is in atmospheric physics. You want to add something to this?
No, what you have said, like I was I would like to just comment that the cloud droplets, again, their formation or dissipation depends on the size of the aerosol. So as he said, like too much, if bigger size, so cloud formation would happen. The cloud droplets will form quickly, and then it will form as a rain. But if the particle size of black carbon is in nano size, it's smaller size, then there are too many nucleating particles, so water will condense, and then the residence time of the particles will be more. So then rain doesn't happen. So that was what he explained, like all the 3 points that I just wanted to add. That size is also an important factor. So it's not just the black carbon or brown carbon, but the size of the aerosol plays an equally important role. So it's not very straightforward to link up lightning and all, because one of my friend used to do lightning. So what I know, that this kind of events are done by bigger models, climate models. So these are not done by observational studies. So
Right.
this is like for an observational experimentalist, this would be like we would not be in a position to give comment on this, actually, how this lightning is related to air quality, because this are coupled with too many micro events. So yeah.
Thank you,
Supriya
Doctor.
wanted to say something. You wanted to add something to this regarding the lightning part.
No, sir. Actually, my thesis was based on the thunderstorm, but not the lightning.
Acha, Supriya, if you remember if you recall the ozone concentration during our lockdown period, and you can easily say the ozone concentration was much higher than the normal days. And that time it was our prediction, because there is less formation and better penetration of sunlight that is causing formation of ozone in the atmosphere. But now today all you have added that brown carbon is also triggering formation of ozone. How we are going to correlate these two? Either Sayantan or also like to discuss this issue, please.
So your query is that increased ozone on the one hand and then reduction of ozone by brown carbon on the other hand. Okay, so the ozone is quite complicated in the troposphere, because for production of ozone you need a large number of things. You need nitrogen oxides, you need hydrocarbons, you need sunlight, UV in a particular range, and there are sort of complex chemical reactions that produce ozone in the troposphere. So yes, if you have increase in the precursors, meaning the hydrocarbons or NOx, these mostly come from cars. greater number of cars, greater is the NOx, greater is the hydrocarbon. So they will produce more ozone in the troposphere. But at the same time, if brown carbon increases, it absorbs in that UV region. So there is less sunlight to kickstart the reaction. So then ozone decreases. Again, so these are the sort of these are the theories that are there in the background. Now, in a particular region, whether ozone will increase or decrease, that is dependent upon the characteristic of that particular region. How much hydrocarbon is there, how much NOx is there, how much sunlight is there. So it is really a local scale issue in that sense, that it will vary very significantly from place to place. It's difficult to give a very general understanding of whether it will increase overall or it will decrease overall. There will be patches.
Now, taking a clue from your thing, the lockdown, the emission was zero, except the domestic. And we came to know the contribution of domestic cooking is around 37%. Now, from this, the concentration of ozone increased, was in the higher side as compared to normal days. Why so?
Yeah, so that is a curious thing that happens mostly because the nature of the reaction that produces ozone is such that unless NOx and hydrocarbons are controlled together, ozone might increase if you decrease one. The nature of the reaction is such. Depending upon whether your location is in a what is known as a NOx limited regime or a VOC limited regime, the production of ozone, the policy has to be made in a very sort of knowledgeable way, in the sense that if that policy is not made in knowledgeable way, reducing one pollutant while actually increase ozone rather than decreasing it. So ozone is a bit tricky in that sense. So my guess would be that it is possible that one of these pollutants went down while the other remained constant or increased, and as a result, depending upon the regime, that led to an increase in ozone concentration, which was unintended probably.
Great answer. Great answer.
I will just add, the reason ozone increased because the biogenic VOCs were continuously emitted, because from the trees, VOCs were continuously increased. So we though reduce NOx, but the VOC increased up because of the by default trees and all, but what we call biogenic sources. So as a result, that was the result why, and this has been seen across many cities. So even the studies are done to see whether the greenery of that particular region during the lockdown has some relationship with the ozone production.
Local factors maybe there, yes.
Yeah.
Thank you, Dr. Safi and Dr. Sarkar. May I request our online participant to please get their camera on for a photograph. And
there is somebody who has written something in the chat box.
Yes, we have a question in the chat box. Murthy, please.
Can you read it?
So yeah, so he's asking whether engaging spectroradiometers for collecting spectra of brown carbon. So the problem here is that this is the same problem that we get when we measure brown carbon using an athelometer. Athelometer can also be used to measure brown carbon absorption. But the problem is that athelometer gives us the total absorption and the absorption by black carbon. So by subtracting these two, we get the brown carbon absorption. But the problem is that the black carbon absorption is so high that we are essentially subtracting two large numbers. And therefore, the result that we get is very uncertain. So you're subtracting, let's say, 27.2 and then 27.3. So this 0.1 is very uncertain.
Yes.
That is why using these sort of instruments is not a good idea for brown carbon.
Thank you. Thank you, Dr. Sarkar, for this enlightening session, I can say. And now, since we are close with the interactive session, may I request Chairman Sir to give his comments on way forward and announce the part 3 of the lecture series, the topic of it.
Thank you, Davinji. First of all, my most sincere thanks to Sayantan, Supriya, and also Professor Gajala Habib for participating in today's deliberations. Very informative informations. We are graduating with time. When I was in school, I heard about dust particles. Then when he grew up, we came across PM 2.5 and 10, things like that. And now we are talking about black and brown. And things are changing. And of course, there are two sides of the particles. One is the health impact, other is the climate change impact. That is true. Actually, whatever you are working, I had flagged this point in a meeting at Kevadia in forest ministers and also all the states. The CPCB is not ready today, as of today, to take up this issue, that there may be speciation of PM 2.5 further into black and brown. Or right, as you said, even in brown, you have so many things. It's not one thing, but a combination of things. I talked about them. The CPCB is straight away say that we are not prepared at this moment to undertake this study. But I'm sure that in future we will have to take it. If we are going to predict the climate change or health impact, it cannot be just size-specific determination, PM 2.5 and 2.10. I strongly disagree. But then whether I agreeing myself or disagreeing never makes the policy. But in scientific community, we are free. We are free to undertake the study. And rightly you are taking this study. So my most sincere thanks for highlighting the things that was close to my heart. And it will be the same series will be going for next session, one more session that will be deliberated by Professor Gajala Habib of Department of Civil Engineering, Indian Institute of Technology, Delhi. And this will be in March.
Yes, sir.
But the date is not finalized. Dr. Saha will in touch with them and will be let you know all the possible dates. And the topic will be conventional sources, apportionment, and use of black carbon data for policy decisions. So at least whatever you are working, I don't know whether you are submitting it to CPCB or not. It will be good if you have publications. You keep sending all the publication to not only CPCB, but also state policy control boards. So that someday policy decision is taken that no, this can be also a part of scientific study that is undertaken by pollution control boards. So the long run it is important. We cannot be stuck up with PM 2.5 and 10. We have to go beyond that. So thanks again to all of you for enlightening us about the aerosol and different aspects. We will be in touch and hope for someday we will have physical meeting also in Patna, where Lord scientists will come together and put their heads and give some policy document to be pursued. Thanks again to everybody.
Thank you. Thank you very much.
Thank you. Thanks to all of you. And with the permission of chair, we would like to close this session
Photographs.
and request all the participants for a group photograph.
Please switch on the.
Please switch on your cameras.
Online participants, please switch on your camera so that we can have a screenshot. Yeah, good. Good. Thank you. Some more, there are Aditi Rana. Two more left.
ठीक है कुछ हो सकता है इसमें. ठीक है.
Okay, take
Okay.
it. Whatever.
Yes. Thank you.
Megha.
ले लीजिए.
Thank you all.
Thank you once again. Thank you all.
Thank you all. Yeah.
I would request our colleagues who are present physically here, please stay in the room for a couple of minutes.